All right, this is going to be an example of how to deal with calorimetry calculations. Calorimetry is easy to understand in the respect that calor means heat and metry means measurement. So we're really studying heat measurement. Now, one of the classic ways that we study heat measurement is with a device called a calorimeter. A calorimeter is basically a sealed container that you have a thermometer in, and that thermometer records readings. And you're, of course, going to have temperature changes when you have those readings. So we have two types of temperature. We have the temperature before, which we call TI, and we have the temperature after, which we call TF. Now, I'm going to fill this calorimeter, and let me label this again. This device we call a calorimeter, and it's used to study heat measurement. I'm going to have water in this calorimeter, and then I'm going to drop a hot piece of metal into the calorimeter. That hot piece of metal is going to fall to the bottom of my calorimeter. And because this metal, and I'm going to call this metal copper, and I'm using the element symbol for copper, is at a much higher temperature than, of course, the water that surrounds it. So what happens over time is the heat energy, the particles from the copper start causing the water around it to move faster, and the energy transfers from the copper to the water. So the calorimeter, say it was starting at about room temperature, 22 degrees Celsius, and say we record its temperature after the copper finishes transferring its energy. We know it's done when it reaches a state we call thermal equilibrium, and that's when we essentially have the copper and the water at exactly the same temperature. So the final temperature, after the temperature stops changing, is about 30 degrees Celsius. And I know that this volume of water is 150 milliliters, which, because it's water and water has a density of 1 gram per milliliter, that means that my water weighs 150 grams. Now, how do we calculate the amount of heat that went into the water? Well, there's an equation that you're going to get very comfortable with, and that's, of course, called, I like to refer to it as Q equals mc delta T. And what this equation does is it allows us to measure the heat that is transferred in a system. Now, this is sometimes written in different ways. Sometimes you don't see a C here, sometimes you see an S. It depends on really what teacher you have, what textbook you're using, but essentially the same four variables are all there. So Q is the letter that we use to talk about heat transfer. So Q is a measurement amount of heat that's transferred, and we measure heat transfer typically in joules in this class. The M represents mass, and we always use grams for mass. The C we like to use for specific heat capacity, and the unit we use it's actually a funky unit, it's joules per gram degree Celsius. And then this thing right here, the delta T, that's my change in temperature. Notice I'm writing the word change. That's because change is what we use the triangle for, which we call delta. So it's delta T, and that of course represents change in temperature. And the unit we use for our change in temperature is degrees Celsius. And don't forget, because it's change, that means final minus initial, so TF minus TI. All right, now I'm actually going to get to work in solving this problem. I've got my picture, I've got my setup, and now I'm going to show you how I want you to actually start writing out your work. Sometimes when you're dealing with an experiment, you have lots of data. You have the data of the volume of the water, you have the data of the mass of the water, you have the temperature change of the water, you have the starting temperature of the metal maybe, and then of course you might also have the mass of the metal. Say the mass of the metal, of the copper, is actually 10 grams. All right, so let's go talk about all this information using a setup I like to use called given formula and work. Given has us take all the information from all the data we've collected and translates it into discrete numbers that we can write down. Let me just show you what I mean by this. Let me just write down all the numbers from that picture that I had previously. So 150 grams, 10 grams, 30 degrees Celsius, 22 degrees Celsius. Those are all the numbers that I have from this picture right here. Now I'm going to start labeling them, and I want to label them as either Q, M, C, or delta T, just like in the equation. And actually, I'm going to write that out as my formula that I'm going to be using in this problem. And the formula, of course, is Q equals mc delta T. All right, so this is grams, these are grams, so they're both mass. So I'm going to label them mass, M. And then these are degrees Celsius, so I know that's temperature. All right, now I've got a problem here. I've got two M's and I've got two T's, so I need a way to be able to tell the difference between the two of them. Well, I know that this was the mass of the water, so I'm going to put a subscript next to that M so that I know it's water. I'm going to use W next to it. That way I know that's the mass of the water. And this is the mass of the copper, so I'm going to write that out as Cu. And then I knew that the 22 degrees was the temperature the water started at, so I'm writing Ti, but because I don't want to mix it up with the metal's temperature, I'm going to write a W next to it. Now this is going to be my final temperature. That's what it got up to, and of course that's the water. And as you see, my thermometer, this little stick that I've drawn in this picture here, it's only in the water. You can't put a thermometer inside metal. It just doesn't work like that at all. So now, let's take a look. I've got all of my data recorded. Now I'm going to put a check mark above the variables that are in the formula that I know the information for and a question mark about what I want to solve. Remember, this question began with me wanting to know how much heat was transferred in joules. So I'm going to put a question mark above the Q because that's what I want to know. I do know mass, so I'm going to put a check mark, meaning I already know that info. And I know my final and initial temperature. And of course, don't forget, delta T is TF minus TI. So I actually already know delta T. So I'm putting a check mark above delta T. Now, the C is specific heat, but you can think of that C as meaning constant because it's a number that doesn't change depending on the substance that you're working with. So for water, the specific heat of water is 4.18 joules per gram degree Celsius. And I always have students say, where did you get this number? And I say, well, it's a constant. And that means that it's something that was measured by scientists, chemists, physicists previously with a great deal of precision. And that number is specific to water, and it never changes as long as water is liquid, and it doesn't matter what temperature it's at. It's always going to have that specific heat capacity. So I actually know that value as well. So now I'm ready to go ahead and plug in my numbers. But we've got a problem here that we have to actually look at. See, I have the mass of water and the mass of copper. When I use this formula, which one do I use? Well, let's look at the temperature we have. The temperature values we have are only for the water. And because they're only for the water, I can't figure out how much heat was transferred in or out of the metal because if I go back to my picture, my measurements were only made in the water. And because my measurements are only made in the water, I can't do this calculation with copper. The mass, the specific heat, and the change in temperature all have to be for the same substance. You can't mix and match. You can't go, the mass is the water and the temperature changes for the metal. It just doesn't work like that. So let's write a note so we remember that. And actually, it's for the whole thing in particular. It's that these variables all need to be for the same substance. All right, now I'm ready to do the last part of this problem, which is what I like to call the plug and chug. What that means is you take the numbers, you plug them into the formula or the equation, and then you solve for what your unknown is. So the work in this particular problem, I'm going to write right below the formula because it's not a whole lot of work. I'm going to write out as Q equal to, notice I have to use the 150 grams, not the 10, times the specific heat, which is 4.18 joules per gram degree Celsius, and then I have the change in temperature, which is 30 minus 22, and I can do that in my head. That's easy. That's only 8 degrees Celsius, so I'm going to write 8 degrees Celsius here. All right, and then I see that my units are going to cancel out. The grams are going to go away, and so are the degrees Celsius. So whatever I get for Q is going to be in joules. So watch how I type it into my calculator. Here's my calculator. I'm going to type in the 150 times the 4.18 times the 8. And then, of course, my answer is 5,016 joules. Now you know how to use the basics of calorimetry. If you have any other additional questions, please talk to your teacher.